So this is 3.2F. So if you don't have 3.2F yet, come and grab one. You should have gotten it last day, but if you did not, please make sure you get one. And this is on page 76. Titration is just stoichiometry. So you remember last year just doing stoichiometry? Titration is just straight up stoichiometry. And you can see I actually even forgot, because I just took this right out of my Chem 11 stuff and I forgot to change the unit. Oh, it was unit 3, but I forgot to change it to solubility equilibrium. So got the wrong title at the top. So basically you're just using conversion factors to go from one solution to a different solution. All right, so you will be starting with a volume of solution A, and you will know its concentration. This is 3.2F, page 76. If you know volume and if you know concentration, that means you know liters and you know moles per liter. What can you find? Everybody. If you know liters and you know moles per liter, what can you find? Moles. Excellent. So you're going to have one substance where you know both the concentration and the volume, and from that you will calculate the moles. All right? The second step is always going to be using your balanced equation, because where does your mole ratio come from? It comes from the balanced equation. And you'll use that to find your moles of substance B, right? So you'll use like the 2-to-1 ratio or the 1-to-1 ratio or whatever it is. And from there, you get to figure out what you are being asked for. You might be asked for the volume of the solution. You might be asked for the number of particles. You might be asked for the mass. But most likely, and this is what we're going to focus on today, you will be asked to find the molarity. So if you have successfully found the moles of B, how would you find the concentration of B? If you know the moles of B. How does one find concentration? Moles divide by liters. So you'll just divide it by liters of B. That's it. Okay, so titration is nothing new or fancy. It's just grade 11 rehashed. So let's take a look at this one example here. It takes 15.6 milliliters of 0.2 molar H2SO4. And remember, the word of connects quantities. So these two go together, yes? And something that's really helpful very often for these questions is to write down what you are given and what you want to find. It just helps organize things a little bit. So we are given H2SO4, and we know that we have 15.6 milliliters, and we have 0.200 molar. We are told our other substance is NaOH, and we are told, what do we know about the NaOH? Yeah, we know we have a 25 milliliter sample, and we are being asked to then find the concentration of NaOH. So we don't know the molarity of the NaOH. The second thing that can also be useful to do is to draw a map of how you're going to get from what you know to what you don't know. So we're going to be starting with our volume of H2SO4, and we'll change it into liters. That'll make life easier, yes? What will we do with our liters? What will step 1 be? We will convert liters into moles, okay? Liters into moles. So we're going to find our moles of H2SO4. Once we know the moles of H2SO4, what are we going to convert that into? Moles of NaOH. And from there, we then at the very end need to find the moles per liter of NaOH, because that is what is being asked for. None of this is required to be written down to get full credit for this question. It's just something that might be helpful to you, okay? So write down what you're given and what you want to find, and draw a little map showing where you're starting and where you're going to. The other thing you need to have for this, because remember, okay, I've drawn all over this way too much. What do we need to convert from moles of A to moles of B? We need a mole ratio, which requires a balanced equation. Okay, so we're also going to have to write a balanced equation if we are not given one. So who are our reactants? Well, we've got H2SO4, and we have NaOH. Any guess of the states of those things? Tell your partner, what do you think the states are for H2SO4 and NaOH? Are they solids? No. Are they liquids? No. Are they gases? No. Are they aqueous? Yes, because we know that they are molar, and molar means it is a solution. So this is aqueous, and this is aqueous. Do you know how to predict the products of a acid-base reaction? It works just like a double replacement. Yes? So you're going to take, what did we do for double replacement? We put who together? The outside ions and the inside ions. So in this case, we are going to have H getting together with OH, which is going to make what? H2O. And then we're going to have our inside ions. The Na is going to get together with SO4. And so what do we get for our other product? Tell your partner, what do we get for our other product? Yes, we get Na2SO4. Okay, and then we need to balance this, because if we don't balance it, then it's not going to do us any good in terms of our mole ratio. So the easiest way to balance it is to say, I need exactly the same number of hydrogens and hydroxides. Yes? Because hydrogen reacts 1-to-1 with hydroxide. You guys know that? Yeah? 1H, 1OH. How many hydrogens do we have here in our reactants? 2. Because the other hydrogen is part of hydroxide. So when I say hydrogen, when we're dealing with acids and bases, specifically that refers to the hydrogens at the front of an acid. Yes, or if it's a organic acid at the end of the COOH. Okay? So how many hydrogens do we have? 2. So there's 2 in our acid. And then how many hydroxides do we have? 1. So what do we need to do with our NaOH to balance this? Remember, you need to make the hydrogens equal the hydroxides. Put a 2. There we go. The other way to do it, and actually I probably should have started with this way because this is actually probably easier, is just to balance the ions that are in the salt first, which would also get you to put a 2 in front of the NaOH. So either way, you can do it either this way, or you can say balance the ions in the salt. Balance ions in the salt. And once you've balanced the ions in the salt, how many water are we going to get? We have, how many hydrogens do we have? 2 hydrogens. How many hydroxides do we have? 2 hydroxides. So how many waters are we going to get? 2. Is good? And if that doesn't work for you, you can always write it as, you could do it like this. H2SO4 plus NaOH. You could actually write it as HOH. Yes? And you could treat the whole thing, balancing and everything, exactly like a double replacement reaction, right? So now we have Na2SO4. And the only thing to remember is that you're treating the hydroxide as a single unit, yeah? So you would balance your sodium, and then you would say, oh, how many hydroxides do I need? I need to have 2 hydroxides because I have 2, so that'll be a 2 there. Okay? So it depends on what you like to do, but it's actually no harder than balancing a double replacement. Okay? So now we have our balanced equation and we've got all our information. Do we want to do it all in one line? Or would we like to just kind of stop when we get to moles and then calculate concentration? All in one line? Okay. So the concentration of NaOH I need to have moles over liters as my final unit. Okay, so that's what I'm aiming for. But what am I starting with? Liters of H2SO4, yes? And so in my head, I do that calculation and I get 0.0156 liters of H2SO4. How can I convert that into the next one over, which is moles of H2SO4? Do we have any information that will allow us to do that conversion? Yes. The molarity, because molarity is moles per liter. And by the way, if you get stuck on this, remember, what does of mean? Of means multiplication. And guess what I'm doing? I'm taking my milliliters and I'm multiplying it by my molarity. I'm actually literally taking 15.6 milliliters and multiplying it by 0.200 moles per liter. And that's my H2SO4. We don't want H2SO4 though, we want to go to our next substance, which is the NaOH. Okay, so we're going to convert that using, how do we go from moles of substance 1 to moles of substance 2? Mole ratio. So there are 2 moles NaOH for every 1 mole of H2SO4. Can I backtrack because I'm running out of room here? So we're just going to go, we're going to find moles of NaOH instead because I have enough room to write this, and then I'll do the concentration on the next line. So this is going to be moles of NaOH because now I've got a string here. Yes, so I can say, okay, my moles of NaOH are 0.0156 times 0.2 times 2, 6.24 times 10 to the minus 3 moles of NaOH. And now we can find our concentration of NaOH by taking our moles, 6.24, times 10 to the minus 3 moles, and dividing it by volume of NaOH. And we can go back to where we organized our information. And we can look and say, oh, look, I know the volume of the NaOH. Yes, so I can just plug it in there, but of course I need to change it to liters. 0.0250 liters. And we get 0.2496 molar. How do we feel about that calculation? Okay. I wonder, did I leave room on the next page for doing it all in one line? Let's check. No, I didn't. That's okay. You could just do it all in one line, and I'll just quickly write that down below. I'll just write smaller. So in one line, what it would look like is we would be looking for concentration of NaOH, and we would have, if you do it all in one line, you don't actually need to change your liters, your milliliters into liters. Ooh, should I do that? Just for fun? Okay. So we have 15.6 milliliters of H2SO4 times 0.2 moles of H2SO4 per liter times 2 moles NaOH per 1 mole of H2SO4. And now this is where some people get like a little bit messed up because they're like, I don't know what to do at this point because I want to have liters on the bottom. So they try and make up something to put on the top. But do we have what we want on the top already? Yes, we do. So we should just leave that alone. Yes? Because we got moles on the top, don't do anything with the top, just put a 1 there, okay? Because all we're doing is we're doing this last division step by dividing by 1 over 25.0 milliliters. And you can see that the millis cancel out if we do that, and you will end up getting exactly that same answer, okay? So if you like that, you can use that, but just remember that sometimes people get messed up trying to do that last like 1 over liters, and if you're good at it, go for it. If you're not, don't worry about it. All right. So here's just some theory behind titration, just to make sure you're familiar with all the words around it. By gradually adding one reactant solution to a precisely measured volume of the other solution, we will eventually hit an end point. The end point is where your indicator changes color. What indicator did you guys use in your titration this year? Do you remember? Yes. Phenolphthalein. And what colors was it? It had 2 different colors. Colorless. Yes, because water is clear, but blue water is also clear. Like if you just put blue food coloring in it, it's also clear, but it would be clear and blue, so colorless. So it goes between pink and colorless. And so you need to know a few terms. The word standard, okay, if we have a standard solution, that means it has a known concentration. So you have to know the concentration of one of the 2 substances. And most often this is referred to as the titrant. So the standard, which is of known concentration, is the titrant, and the titrant goes in the burette. There is also the other solution called the sample, and it has a known volume, but it has an unknown molar concentration. That's the one we're trying to find the concentration, and it is also known as the analate. But I don't think you're going to hear that word that often, okay? Analate. Even titrant, in grade 12, you won't hear it that often, but if you do go to do a lab course at university, we will hear these words more often. Do you remember what a burette looks like? Describe to your partner what a burette looks like. Yes, I'm seeing lots of this, right? Yeah, because it is that big long tube, and at the bottom it has a stopcock that it's the valve that lets out the liquid, and it shows the volume of a liquid that has been let out. An indicator, that is that substance that changes color according to the concentration of the chemicals that surround it. So for example, phenolphthalein, if it is surrounded by acid, it is colorless. If it is surrounded by base, it is pink or magenta. Okay, so it just depends on what kind of environment it's in. There are some self-indicating reactions where the reactant actually changes to a different color when it's a product. And we'll be doing one of those in Unit 5. The equivalence point, which is also known as the stoichiometric point. That is the point at which substance A and substance B have completely reacted. There is no leftover of either reactant. So if I put 10 moles of my HCl into the flask, how much NaOH would I have had to add? It's a 1-to-1 reaction, by the way. I would have had to put in 10 moles to get it to react perfectly, okay? And if I had like a 2-to-1 ratio, I would have had to put in like twice as much, yes? Unfortunately, these two different points, the equivalence point and the end point, both start with E, so often people find it confusing, and they think that they are the same thing, but they are not. The equivalence point is when the reaction is complete. Technically, you don't need an indicator for an equivalence point to occur. Yes? You just won't be able to tell when it happens, right? You'll be like, wow, I just don't know when I hit that equivalence point. Yes? The end point, which is the other kind of point, that is to do with the indicator, and it's when the indicator changes color. It is possible to choose an indicator that will change color before you get to the equivalence point. Would that be useful? No. Okay, so choosing the correct indicator when we get to the acids and base unit, that will be something that we actually focus a little bit on, is just how do you choose an indicator that actually matches up with the equivalence point. Okay, but solubility titrations, doesn't matter. An outlier. Are you guys familiar with outliers? Outliers are titration values that don't agree with the rest of the trials. So in any titration, just like the ones you did, how many trials did you do approximately? Like somewhere between like 4, 6, maybe if you had a larger group, right? You will always be doing multiple trials because you'll get better data if you do an average of a bunch of different tests. But if you have one that does not match close enough, and sort of an arbitrary value that we've chosen is 0.2 milliliters, if you actually go and do real lab work, you'll learn statistical analysis that will tell you like, oh, these ones are close enough together and that one is an outlier. But for Chem 12, we're not going to do the statistics, so we're going to say within 0.2 milliliters, okay? So here's a little picture of titration, which is nice to refer to. We have our standard solution. Is the standard the one you know its concentration, or is it the one you don't know? Standard we know, okay? So there's our standard. It is known, and we can also call that the titrant, and it goes in the burette. The sample that's the one where we don't know the concentration. It might also be called the analyte, and it goes in the, oh, I didn't label this. What is that thing there? That piece of glassware? That is an Erlenmeyer flask. Okay, and the indicator also goes into the Erlenmeyer flask. Did anyone try a titration this time and forgot to put in the indicator? That's always great fun, because you're like, oh, why hasn't it changed color yet? Did we put in the indicator? Oh, oops, right? We've all done it, at least wise I have. And then we drip, 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 drip. So we measure our initial volume. That can't write. That doesn't look like initial. Initial volume, and then somewhere or other we'll finish and we'll get our final volume, and then we'll find our volume delivered. How do we find the volume delivered? How do we find how much was dripped out of the burette? Final minus the initial. Okay, just a quick reminder there that that's how you do that. And you repeat this process with at least 3 volumes until at least 3 volumes are within 0.2 milliliters of each other, or if you're in high school, until you run out of time, because sometimes you don't get that many that close to each other. Any volumes that aren't are, of course, those outliers, and you do not use them in the calculations. So you will exclude any volumes that are not within those 0.2 milliliters, so those would be your outliers. So when you're calculating your average, you're going to toss that one out. So if you have 4 data points and one of them is not good, you will only average 3 of them. And then you just do the calculations along the lines of what we just did. Do you want to go through like an example? I just took, like I said, I just took this full from grade 11, but maybe we don't need this whole example. Maybe we don't. Yeah, okay, good. All right. So there are some exercises here that you can try if you want to practice it. However, there is also, hey, where did it go? 3.2G, which specifically has solubility titrations. Yes? And it has on page 80. On page 87, if you forget what to do, you can check there. There's a list of the steps to do. And you could try some of the problems that are on that back page. Should we do that? Okay, excellent. So try some of those on page 88. Oh, and the only thing I forgot to mention is when we're doing solubility titrations, sometimes you'll have like reactant plus reactant, and then it's like a normal double replacement. Other times they might give you reactant and just the other ion. If that's the case, you can just get rid of that NO3 because it's a spectator and just work with your net ionic equation. Okay, and if you're confused by that, you can call me over and I'll help you out with it. Alrighty, so give those a go. There's another solution then. Let's see.